हेलो शजील।
अस्सलाम वालेकुम, कैसी हैं आप मैम?
मैं ठीक हूँ, आप सुनाओ।
मैम अल्लाह का शुक्र है, ठीक।
गुड। हेलो रामीन।
मैम ये हमारी लास्ट क्लास है मिड से पहले।
आई थिंक सो, यस, मिड आपके ट्यूसडे को है।
यस मैम। तो मैम फर्स्ट 3 चैप्टर्स।
जो कुछ हमने पढ़ा है, नो, नॉट फर्स्ट 3 चैप्टर्स, ये अब जो पढ़ रहे हैं वो भी शामिल है।
कप्लान वाला भी, चैप्टर 10 भी।
हैं?
मैं कप्लान वाला ये चैप्टर जो हम पढ़ रहे हैं, न्यूक्लियर रिएक्शंस, ये भी इंक्लूड हुआ है नहीं? हाँ,
हाँ जी, बिल्कुल बिल्कुल, यस।
ओके मैम।
हेलो रामीन। हेलो।
तो मैम अगर हम यही चैप्टर जो है उससे पढ़े
कहाँ से?
क्रेन से, तो उसमें तो कोई ज्यादा डिफरेंस तो नहीं है, आई मीन बुक से।
आपके पास क्या प्लान नहीं है, आप इसलिए कह रहे हो या
मेरे
मतलब?
मेरे 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 पास
हाँ
के प्लान में सॉफ्ट में तो ले लूंगा, मैं डाउनलोड कर लूंगा, लेकिन वो मैंने क्रेन की ली हुई थी, इसकी मैं पूछ रहा हूँ।
हाँ हाँ हाँ, नहीं ठीक है, इट्स फाइन, आप दोनों से पढ़ो ना, क्योंकि कुछ चीजें यहाँ से आंसर हो जाती हैं, कुछ वहां से आंसर हो जाती हैं, ठीक है ना।
नहीं, मैं देखना चाह रहा था कि ज्यादा फर्क तो नहीं है, इसलिए पूछ रहा था मैं।
वो तो मतलब ऑफ कोर्स जितना आप पढ़ोगे उतना फायदा। ओके, ठीक है ना।
यस मैम।
हम्म,
यस मैम।
अच्छा जी। सो रामीन का माइक नहीं चल रहा।
हेलो मैम।
हेलो रामीन, क्या हाल है?
ठीक, बिल्कुल। आप कैसी हैं?
मैं ठीक हूँ, अब बाकी लोग कहाँ हैं? जल्दी से बुलाओ ना ताकि हम स्टार्ट करें।
ओके मैम।
मैम कैसा गुजरा है आपका लॉकडाउन? बोर होती होंगी घर पे आप भी हमारी
नहीं,
तरह।
बोर होने का टाइम नहीं है, सॉरी, आई हैव अ लॉट टू डू। ऑनेस्टली। आप सुनाओ, आपका कैसा जा रहा है?
मैम बहुत बोरिंग,
आप
मैम
बोर हो
यकीन
रहे
करें घर
हो,
में
है
पढ़ने को
ना? या
बिल्कुल दिल नहीं करता। यस मैम, बहुत इंसान पढ़ने बैठता है तो घर में कभी कोई काम आ जाता है कि शोर होने लग जाता है।
हाँ, ये
तो मैं
है।
तो दिन में सोता हूँ, और फिर रात को फिर वैसे ही इंसान कहता है यार ठंड बहुत है, रहने दो।
अच्छा अच्छा, राइट, सो दैट्स द इशू के दिन में मतलब यू कैन नॉट कॉन्सेंट्रेट, तो यू
यस
हैव
मैम।
टू सी हाउ यू कैन वर्क अराउंड दिस, किस तरह से किया जा सकता है ना, कोई ऐसी जगह जहाँ पे आप खामोशी से बैठ के पढ़ सको, बिकॉज वही बात है कि आपकी नींद नहीं पूरी पूरी होगी, तो दैट्स आल्सो नॉट गुड फॉर हेल्थ, यू विल बर्न आउट, ठीक है ना।
मैम बस बहुत अजीब
नहीं,
अजीब
आई वुड
सिचुएशन
नॉट
है, पहले
सजेस्ट
वाला जो
कि
था ना,
आप,
पहला लॉकडाउन अच्छा गुजर गया है।
पहला क्यों अच्छा गुजरा था?
मैम उसमें यानी कि स्टडी काफी हद तक अच्छी हो गई थी, इस दफा तो यानी कि इतना कोई खास अभी तक कंसंट्रेशन तो की नहीं। अभी तक तो बस गुजारा हो रहा है।
अच्छा, नहीं, आप देखो क्या इसके लिए हो सकता है, हाउ, ये अब आप ही को पता होगा, आपकी सिचुएशन में हाउ यू कैन ट्राई टू फाइंड अ प्लेस जहाँ पे आप कंसंट्रेशन से बैठ के काम कर सको, पढ़ सको और सो भी प्रॉपर सको, राइट। सेक्रीफाइसिंग योर स्लीप इज नॉट गुड, इससे बहुत प्रॉब्लम्स लॉन्ग टर्म हो जाते हैं फिर, ठीक है। रामीन, डिड यू सेंड अ
यस
मैसेज?
मैम।
यस मैम।
अच्छा, आप लाहौर में हो शजील?
सो मैम पेपर हम, नो मैम,
कहाँ पे हो?
मैम आई एम फ्रॉम उकाड़ा।
ओकाड़ा। वैसे हॉस्टल में कुछ स्टूडेंट्स को ऑफर की गई है रहने की, अब आई डोंट नो इफ दैट वर्क्स फॉर यू।
आई डोंट नो मैम, बट उन्होंने इस दफा न्यू स्टूडेंट्स को रखा नहीं, यानी कि जो ओल्ड थे उनमें से कुछ को रखा था।
नहीं नहीं, वो जैसे हमारी क्लास में कौन रहता है, रामीन रहती है। रा,
यस मैम, उसका
यस मैम, लेकिन
परमिशन है।
हाँ, परमिशन है शजील। इफ यू, मतलब ऐसे स्टूडेंट्स को अकोमोडेट किया गया है कि जिनको प्रॉब्लम है कोई, एंड दे आर नॉट एबल टू पार्टिसिपेट इन स्टडीज ड्यूरिंग द लॉकडाउन, तो
ओके मैम, मैं मेल करूंगा, देखते हैं क्या कहते हैं
मतलब यू हैव टू
यूनिवर्सिटी
आल्सो
वाले।
एक्सप्लेन व्हाट्स योर प्रॉब्लम एंड व्हाई यू वांट इट एंड सो ऑन, ठीक है।
मैम
मोस्टली
स्टूडेंट
तो
के
वो
पास सारी
वाले
प्रॉब्लम्स ही होती हैं, सॉल्यूशंस तो होते ही नहीं है।
नहीं नहीं, सोल्यूशन खुद निकाल दिए ना, तो मोस्टली दे अकोमोडेट स्टूडेंट्स हु आर फ्रॉम एरियाज जहाँ पे इंटरनेट इश्यूज हैं, ठीक है ना, वहाँ से वो मोस्टली अकोमोडेट करते हैं स्टूडेंट्स को।
लेकिन मैम हमारा ऐसा कोई सीन नहीं है, बस घर में पढ़ने की रूटीन सेट करना बहुत मुश्किल हो जाता है।
नहीं, अब यू हैव टू वर्क, ये अब एक दिन की बात तो नहीं है ना, ये हमें नहीं पता कितनी देर आपको ऐसे।
यस मैम, गुजारा तो हो रहा है, लेकिन वो फिर हॉस्टल में तो जिस कंसंट्रेशन के साथ जो होती है ना, वो सारी घर आके अचानक से खराब हो जाती है।
मैम चांसेस हैं कि छुट्टियां ज्यादा हो जाएंगी?
छुट्टियां कैसे ज्यादा हो जाएंगी? यू कॉल दिस छुट्टियां?
नहीं मतलब कि ये कोरोना वगैरह।
कौन बोल रहा है? रामीन?
रामीन।
बेटा वी डोंट नो, नोबडी नोज एक्चुअली, डिपेंड्स ऑन द सिचुएशन।
ओके मैम।
अच्छा, सो लेट्स सी। हेलो दुर्दाना। हेलो
Can you hear me?
दुर्दाना बोल रही है?
Yes, ma'am.
ये कौन एंटर करना चाह रहा है हमारे रूम में? इसका आईडी है क्यू कॉम। अब दिस इज अ स्ट्रेंज आईडी, अब आई डोंट नो दिस पर्सन। ग्रुप में मैसेज करके पूछो हु इज क्यू कॉम डैश बीटीडी। आई कैन नॉट एडमिट अ पर्सन आई डोंट नो, ठीक है? मैंने आपसे पहले भी कहा था प्लीज अपने आईडीज ऐसे अपने प्रॉपर नाम के साथ बनाओ, राइट? टेल दिस पर्सन टू चेंज टू हिज और हर प्रॉपर नेम। कौन है क्यूकॉम डैश बीटीटी को? मैं नहीं जानती। ओके ओके सो
Ma'am, I've sent that message in the class group.
good, great. Okay, now we can start. If this person changes their name and we can recognize him, we'll let him in, otherwise no. And I'm going to share my board with you. Okay, so can you see the board?
Yes, ma'am.
Yes मैम।
ठीक है? Okay. So we are talking about we talked about nuclear reactions. Today we are talking about, let's first talk about just a small concept that we come across, which is attenuation. So what do you understand by attenuation? What do you understand by attenuation?
No idea.
Never heard of it?
Yeah, ma'am. I guess
No,
not.
ma'am.
I'm
Okay.
not remembering
So
it.
we have all students in the room except Aman. अब आप पूछ लो Aman को मैसेज करके वो किस आईडी के साथ ज्वाइन करना चाह रही है, and tell her to rename herself. Okay? If this is Aman. Okay, so attenuation means the reduction of a radiation quantity. Okay, so it's a reduction of a radiation. Yeah, now this is Aman. Okay, of a radiation quantity. Okay, so we are as radiant energy in terms of radiant intensity. Okay, or it may be a particle flux density. or it may also be in terms of energy flux density. Upon the passage of the radiation through matter, okay? So it may be result from any kind of interaction with matter, such as absorption, scattering, etc. So any kind of interaction, okay? In any kind of interaction. Like absorption, scattering, etc. Okay. So in for example, in the case of an electrical circuit that you're familiar with, attenuation would mean the reduction in current or voltage or power along a path of energy flow. So in this case, we are talking about radiation attenuation. Okay, that's the difference. So that was the electrical concept, was just an example. We are using this term for radiation attenuation. We know that whenever a radiation is incident on a material, okay, then the intensity of this radiation after passing through the material will decrease. And the reason for this will be that some of this radiation might have absorbed and some of this radiation might have scattered. So whatever happened inside, since we talked about nuclear reactions, so whatever happened with the atoms and the nuclei and so on, in this case, the radiation, this is the radiation and this is the material. What is material? Matter is composed of atoms which are composed of nuclei. So this is an example of a nuclear reaction. So whenever this happens, there is attenuation, and attenuation means that there will be a reduction of the radiation intensity or the radiation flux density, radiation or particle in both cases. You know, when we talked about interactions, we said it was x plus x will give you y plus small y. So this x is the radiation. It can be gamma rays, for example, okay? It can be any other kind of radiation, but it can also be particles like alpha, beta, and it can be a neutron, and it can be a proton, it can be an electron, it can be a photon. So any particle or radiation incident on matter will interact with that matter, and there are many different kinds of interactions that can take place. And as a result of those interactions, if we combine those interactions into two main categories, we can combine them into absorption and scattering. So it means that the material will absorb some of this radiation, and the second possibility is that some of this radiation will scatter. Now there are different kinds of scattering that we can look at now, but as a result, the radiation that leaves the material will be less in intensity or less in flux density or less in the energy as compared to the incident radiation, and this is known as attenuation. Is that clear?
Yes, ma'am.
Good.
Yes, ma'am.
Good.
Yes, ma'am.
So now I am going to the topic, the main topic for today, which is, so this is nuclear cross section. It's called nuclear cross section. Or it's called reaction cross section. Just as I said before, cross section, what was the definition of cross section I gave you before?
The probability of reaction.
Yeah.
Was something like.
Yes, it's the probability of occurrence of a nuclear reaction. Okay, and its unit is, what are the units? The units are barn. Now, barn is a very, it's not a very scientific term. In fact, a scientist just came up with this word. It's just a normal language word, which means barn kya hota hai वैसे? What is a barn? A barn is?
Barn is usually a place where horse fodder is put, and this is where
Yes,
they eat.
yes, great, yes, good. So it's a shed-like structure, a storeroom for grains, mostly that farmers have in villages, right? Or like you said, for horse fodder or whatever, right? So it's just a structure that they have for storing something. But, you know, scientists can name it whatever they like. But if you want it, you know, sometimes we have some terms that are not very scientific, but we still use them. But then we also have the scientific definition, which is one barn is defined as 10 raised to minus 24 centimeters squared, and this is equal to 10 raised to minus 38 meters squared. Okay, so this is the unit. Okay, now what does the nuclear cross section depend upon? Okay, so let's talk about this. Nuclear cross section depends upon the kinetic energy of the incident particle, okay? So the kinetic energy we know depends on the speed of the particle, right? And for example, if a particle is moving with a speed of, let's say, 10 raised to 3, okay? So for example, if the speed is, let's say, 10 raised to 3, the cross section would be, we can say, 1200 barns. And if the speed changes, let's say to 10 raised to 4, the cross section might be 120 barn. This example indicates that the cross section is dependent upon energy of the incident particle. So which means the energy of the incident radiation, right? So higher is the energy, lesser is the cross section. Okay?
That's very interesting.
That's interesting. That's very, very interesting. Okay. So
does it happen because a slower particle has more time to interact with the
yes,
nuclei?
exactly. Yeah, that's one of the reasons.
Oh.
Yes. Also, you can imagine like the simple example that we used to give in basic physics, which was the collision of balls, right? The billiard ball example that we have. Okay.
Yes, ma'am.
Yeah, okay. So one of the factors on which it depends is energy. This is a very important factor because when you look up into tables, you have, I think, a table in your book also, where you can look up some values of cross sections. You can look up some databases. There are some well-known databases that I've been telling you from time to time, like the NIST databases, the IAEA databases, maybe CERN also has it. So in this case, you can find these values that different scientists have measured and calculated, and they are accepted as the values. But you also have calculators available online from very authentic sources. These calculators are based on algorithms and simulations, whereby you can enter your reaction and you can see they will give you as a result, they will give you a graph of the cross section. So the graph would mean that it will be dependent upon energy, okay? So energy or wavelength or speed, the energy, wavelength, speed are all interrelated, right? So one of these parameters will be on the x-axis, and then you will have the cross section on the y-axis. So it means it's a value or it's a quantity, it's a parameter that depends upon the energy or the speed or the wavelength of the incident particle or radiation. So this is a very important point, okay? The second is the nature of nuclear reaction. So what kind of a nuclear reaction is that? So nature of a nuclear reaction would mean what is X and what is capital X. Of course, you have to know this in order to determine. This will make a difference. The incident particle, what it is, would make a difference, and the target nucleus, what it is, would also make a difference. So these are the two main points, okay? And now we can go towards finding the expression for cross-section. Cross-section, as I told you, is a term which is not very straightforward. It's a little bit abstract, so we'll try to explain it. So let's look at the expression for nuclear cross-section. Okay. So for this case, I would like to show you a figure. Cancel. Okay. So this is page 458 of Kaplan. I'm taking this figure from there. Okay, so it's not very clear, but anyway, you can see it. So let's share this. This is the figure we're talking about. Okay, so can you see the figure?
Yes, ma'am.
Yes, good. So this is
Yes, ma'am.
this is the material that you can see over here. So you had your standard reaction, which is something like, okay, so you had X plus capital X will give you whatever. Okay, so in this case you can see X is your small particle that's incident on a nucleus. That nucleus is in some material, so this material has been represented here. Okay, a nucleus normally exists in some material. It can be if you look at the fission reaction, for example, this could be a neutron interacting with the fuel, which is uranium, but uranium will be in the form of a pellet or in the form of a rod. It may be inside that, so it will be in some shape. So the shape we have considered here, and this shape will contain more than one nuclei. There will not be a single nucleus, right? So we have this material in the form of this cuboid over here, and we can see that the incident radiation and the neutrons that are bombarded are not again one single neutron. You normally have a source of radiation, and it's giving off some radiation. So you have a certain number of particles per centimeter squared per second, which is known as the flux. So this radiation flux is represented here. So this is the incident particles coming. Okay. Now these incident particles have a velocity which is v. Okay. And the number of particles per, just a moment. Okay, right. So this flux is given here, and you can see that n is the number of particles, v is the velocity of the particles, a is the area of this material that is exposed to the radiation that is coming, and the surface density is defined here, the number of nuclei is here, and the nuclear density is here. Okay, so let's start from here and try to find the expression. So if we say that capital R is the radius of the nucleus, then we can say sigma is equal to, okay, that's let's not go there yet. So let us consider a thin sheet of the material. So you can imagine this to be a thin sheet which has a thickness T. So let's assume that this is a small thickness. And it has an area A, and the number of nuclei is NT. This is the number of nuclei NT. So probability of collision, probability of colliding would be probability of colliding or collision would be given by NT sigma divided by A. So sigma is the cross section. Sigma here represents cross section. Okay. Again, you know, whenever we develop some expression or some derivation or some equation, we always make a number of assumptions in order to make it simple. Okay. So in this case, also we have an assumption. One assumption is that this is very thin. The second assumption is that these nuclei are not overlapping each other, whereas you know that in reality they would. Okay. So NT over A is the number of nuclei per square centimeter. So NT divided by A is the number of nuclei per centimeter squared. Okay. And this is also called the surface density of nuclei. This is square and density of nuclei. Okay. And therefore, we can say that NT over A can also be written as N multiplied by small t, where T is the thickness. T is the thickness. So please remember there's a difference between the small t and the capital T. N, we have already defined N. N is the number of nuclei per cubic centimeter. N, it's defined here. N is the number of nuclei. N is number of nuclei per centimeter cube. Okay. So for an incident beam with N particles, the incident beam, the total number of particles in this beam, let us say, is N, like we have written over here, small n. Now please distinguish between small n, capital N, small t, capital T, and so on. So the number of particles in the incident beam is small n, and so n is the number of nuclei per centimeter cube. So n is the number of these nuclei in 1 centimeter cube volume, okay? Whereas small n is the number of incident particles in the beam, okay? So, and we have already said that they have a velocity v, and the number of particles passing through the sheet will be given by nv per square centimeter per square per second. Okay, now I'm going to go back to my board because I don't have any space anymore. Okay, so I'm going to go to the board here. So let us write the expressions that we have that we just discussed. So we talked about probability. Oh, Okay, so my meeting is going to end in a few minutes, and when it ends, please click the same link again. Okay, is that clear?
Oh, okay, ma'am.
Okay, right. So we
Yes,
said
ma'am.
the probability of colliding was NT sigma over, sorry, this T is a subscript, okay? NT sigma over capital A. And then we have NT over A is the number of nuclei per centimeter squared. And then we also called it the surface density of nuclei. And then we said that NT over A is equal to N multiplied by small t, which is the thickness. And N we said was the number of nuclei per centimeter cube. And similarly, we said that small n is the number of incident particles having a velocity v. And therefore, now we can write the collision rate based on these. The collision rate will be given by collisions per square centimeter per second. Okay. So collisions per square centimeter per second will be given by collisions per square centimeter per second will be given by NV sigma, capital N into T. And therefore we can say that sigma is equal to collisions per square centimeter per second divided by NV multiplied by NT. Okay, and then NV is the number of particles in the incident beam. NV is the number of particles in the incident beam crossing 1 centimeter square of area each second. So NV therefore is the particle flux. This is defined, the definition of particle flux. Hence, this equation shows that the cross-section for collision is the number of collisions per unit volume per second for unit incident flux and the unit nuclear density. So we can conclude this from here. The term collision can be replaced by the appropriate term for any nuclear process. So we use the analogy of a collision just for simplicity, just for understanding. Actually, this is a nuclear process we are talking about, okay? So I'm going to erase this. So in this case, we can say that sigma S with this is a subscript, okay? Sigma was the general term, just cross section, and sigma S would be the cross section for scattering. Okay, and sigma scattering would be equal to sigma elastic plus sigma inelastic. So as we know that there are different kinds of scattering, and the main types are the elastic and the inelastic. And similarly, as we said in the beginning, when we were talking about attenuation, there is a possibility to have an interaction in which there is absorption. And for that case, again, we can define the cross section as sigma A. So sigma A is absorption cross section. So this means the number of particles that are absorbed or that disappear per centimeter cube per second for unit incident flux and unit nuclear density. So similarly, cross sections for individual reactions, like we studied the different types of reactions. So the cross sections for each reaction each kind of reaction can be written like this. So this is a cross section for a alpha P reaction. Alpha P reaction means a reaction in which the incident particle small x was alpha and the product particle small y was a proton. Similarly, you can write it for another kind of reaction, which is an alpha N reaction, in which case the incident particle was an alpha and the product particle in the end was a neutron. Or you can have another kind of reaction where you have sigma p alpha. In this case, the incident particle is a proton and the emitted particle is an alpha. So these are the different kinds. So we saw that cross section depends upon, we said energy, right? Energy is related to velocity, which is also related to wavelength. So that was one main criteria. And the second was on the nature of the reaction. Nature of the reaction depends on the incident particle that is being bombarded and also on the target nucleus. So these are some examples of the types of interactions that can take place. So the main types of interactions have been divided into absorption and scattering. Scattering is further divided into elastic and inelastic. And now we can go further and combine them in order to write an expression for cross section. Okay. So I'm going to end the meeting here, and then I'm going to start a new meeting again by clicking the same link. Okay. And you can do the same.
Oh, okay, ma'am.
Okay.
Oh, okay, ma'am.
Okay, beta.
Okay, ma'am.